jumping on the first punch there. All right. We go from current slide. And remind you, now you've got around 3 weeks left until college transfer days are happening. That's Wednesday, February 12th, 9:30 to 11:30 on the Birmingham West Campus, the Academic Building, B Hall. Okay? And then on Thursday, the 13th, from 9:30 to 11:30 here on this campus, and I believe that's going to be in the faculty staff dining room. They say the campus cafeteria, but that's awfully crowded for the end of breakfast and beginning of lunch for them to be taking that many tables in the cafeteria. So I'm guessing it's in the faculty staff dining room. Lots of universities and colleges have been invited. Don't know who all will be here, but it'll probably be a pretty good number. And then I really encourage y'all to look into the summer research program at the Center for Power Optimization and Electrothermal Systems, POETS. That's at University of Illinois, Arkansas, and Howard University. 10-week internship exposes students to academic research in the fields of mechanical, electrical, and material engineering. Students are paid $5,000 stipend. Now, if that seems pretty amazing to you, here's the deal, folks. The U.S. is desperate for engineers, okay? It is one of the most in-demand fields that we have. We're having to import engineers from other countries, India, China, and probably others as well. It's getting harder and harder with some of our immigration policies to attract the people that we need. So they are really desperate for engineers. So please take advantage of things like this that can give you a good step forward in a really great career. Okay? The deadline for this application is February 15th. And I have 2 pages, a page and a half of information here, and a little brochure here. Most of the information will be on the inside page of the brochure. The outside I can hardly read. Maybe you can make more out of it than I can, but it was just really lousy. They did a blue background with sort of faded white, and then they printed in white, and it's just really hard to see. But I think all the information you need is inside. So you're welcome to look at this anytime you wish. All right. No new folks getting here. Believe we are, I know we're in chapter 11, vectors in geometry of space, 11.1, vectors in the plane, 2-dimensional vectors. And we had done, I believe, example 5. And I can't see where this slide is. I see standard unit vectors. Oh, okay, it's the top of the next page. Seems like we did not do this little blurb underneath example 5. Okay? So let's fill in the gap here. Here's example 5. Well, let me get my pen set up. Okay. Any questions before we get started? I don't know about y'all, but it feels a little chilly in here to me. Yeah, okay. So, anyway. Let's say let U, what does that symbol mean when I use it? What typically doesn't use it? Unit vector, yeah, unit vector. That U, and it says be a unit vector, okay? Okay. And theta is the angle measured counterclockwise okay, that's pretty lousy writing, but I hope you follow it. Measure counterclockwise from the positive x-axis to u. Okay? So here's the illustration of it. If this is the vector u, unit vector, so it's on the unit circle, theta is the angle measured counterclockwise from the positive x-axis to u. Then the terminal point on u lies on the unit circle. This is a circle 1, 0, 0, 1, negative 1, 0. My drawing isn't good, but I'm trying to fill in the gap. 0, negative 1. Okay, unit circle. Then this vector u can be represented always with this setup that we have here as the vector cosine u, cosine theta, I'm sorry, sine theta. Okay, now why is that? Okay, hopefully you'll agree with me. This is the x component of that vector. That x component will never be greater than 1 or less than minus 1. Okay? And the x component is, if this is the angle theta, it is the cosine of the cosine of theta is equal to this x value divided by its hypotenuse, which is always 1 because that's a unit vector. And the y value is, this is the y component of that vector. It's always going to be the sine of that vector. The sine of this angle is the y value over 1. So that's why that's cosine theta, sine theta. Okay. Or you could write this as cosine theta I plus sine theta j. Both of those are unit vectors. Okay. Goodness, I'm cold in here. Moreover, it follows that any non-zero vector v is not the zero vector. Okay. Okay, v is not the zero vector, excuse me, making that same angle theta with the positive x-axis has the same direction of u. So v could be that vector, or it could be that vector, okay? Either longer or shorter than 1, doesn't matter, making that same angle with positive, okay, has the same direction of u, and you can write that then v, the vector v, is equal to the magnitude of the vector v times vector u, which you could write this way, cosine theta I plus vector v, I don't know why they write it this way, but they do, times the sine theta j. Okay. Now, hands are cold, everything's cold. All right. That in mind, let's do example 6. It's not on the slideshow, so let's us do it, and we'll do it here if we have room. I think we do. A vector v has magnitude of 3. So how can we represent that? That vector v's magnitude is 3. What's the symbology for that? How do we express the magnitude of a vector?
It's like 2 lines.
Yes, it's sort of a double absolute value looking line is equal to 3. Okay, magnitude of v is equal to 3. And it makes an angle of 30 degrees, so your theta here is going to be the 30 degrees or pi 6 radians, whichever you choose, with the positive x-axis. Write v as a linear combination of the unit vectors I and j. So we want to write v as some coefficient times I plus some other expression times j. Okay. What would be the fill in the blank there?
Cosine theta pi.
Okay, certainly cosine theta, and theta happens to be pi 6, so I'm going to put cosine of pi 6, but I need something else. 3 times 3 plus okay. Now the next question is, how much is pi 6? The cosine of pi 6.
Root 3 over 2.
Okay, cosine being the, root 3 over 2. So this will be 3 times root 3 over 2i. Help me with the next part. Say again.
3 times root 3 over 2 times j.
Okay, sine of pi 6 is the same as cosine pi 6. Oh.
3 times 1/2.
Which you could write as 3/2 j. Okay? Believe you have it not there, and you do. That's exactly what they have. Good deal. All right. Now we can move. Any questions on that for you?
Just leave it like that.
That's perfectly fine. It's a linear combination of the unit vectors I and j. Yeah.
So for the linear combinations,
Right.
all the answers have to have something I plus something j, right?
That's correct.
Okay.
And the linear part, I don't want to say this always, but it implies that there's no, there could be a number squared or something like that, but certainly no variable squared or other things like that, then it wouldn't be linear. So just a number, yeah, okay. All right, good question, good observation. All right, then we get to vectors have many applications in physics and engineering. One example is a force. A vector can be used to represent a force because a force has both magnitude and direction. Not just force, velocity, displacement, acceleration, momentum, probably others, I'm just not thinking of any now. Torque, all those things are vector quantities. If two or more forces are acting on an object, then the resultant force on that object is the vector sum of those vector forces. Okay? Same thing we were doing before, but now putting a practical twist to it. What do they actually do? I'm going to give you a really dumb example, but it did happen. And we thought to it before we did anything stupid with it. But when we first moved into the house where we currently live, the previous owners, the house was in pretty good shape, but they kind of let the yard just grow up however it wanted to. And we loved the yard because it had lots of trees, but we really had too many trees. There were specifically 2 little pine trees that were growing up under a pretty good-sized oak canopy and pecan canopy. And those little pecans were just twisting and turning, trying to find a way to the sun. They were ugly little trees, but they had just left them there growing. And they had gotten pretty tall, very thin, because they were trying to reach for the sun, but very, very misshapen, just not great trees. And we had not been in there long, and my wife's father came down with his chainsaw from Huntsville. I hadn't bought one yet. And also her brother-in-law from Huntsville came down with him, and they were going to help us get the trees down. So we threw the house sitting right there. We had other plants there. We wanted to be very careful where those trees, which direction they fell, because they were already leaning pretty badly. We wanted to make sure they fell where we wanted them to, not where they were going naturally. So we took and stretching for the sun, the lowest limb on the tree was way up there. So we threw a rope, took us a few tries, as high as we could, and did get them to go around the tree where the top bough limb came down the other side. So while Mr. Brazil handled the chainsaw, Dan and I, my brother-in-law and I, took each end of the rope. Yeah, it was long enough for us. Now, to get maximum pull on these, we should have pulled in the same direction, right? Then you just add the 2 vectors together. What's wrong with that picture? The tree would fall right on top of us, okay? So, we didn't want to do that. So we got a little bit of an angle in between, enough of an angle so the canopy of the tree would come down between us, okay, without hitting either one of us. So we did like this. Now we lost some pull there, because when you add this vector to that vector, the components of the vector in this direction and that direction, this direction and that direction, these two basically almost cancel out, okay? But you add the 2 components here. That's an example of a resultant force. You add them by components. Everything you do by components. If you haven't gathered that. So let's see their example. Here are 2 tugboats pushing an ocean liner, as shown in this figure. Each boat is exerting a force of 400 pounds. 400 pounds pushing an ocean liner. That seems a little on the weak side to me, but maybe not. Yeah, okay. And it says what's the resultant force once Fred gets here of, and no one, so Fred wasn't here pushing on the ocean liner also, okay. What's the resultant force on the ocean liner, okay? Now, they showed these 2 tugs, and I can't think of a specific reason except possibly the stern of this boat is curved, and they wanted to push perpendicular to the curve, so they chose to do 20 degrees, okay? This one's pushing in this direction at an angle of 20 degrees from the horizontal, the way we've drawn it here, and this one's pushing in this direction, which is 20 degrees below, so they put a negative 20 there. Now, each of these forces is 400 pounds in the directions indicated. Now, what's the resultant force on the ocean liner? Again, you add the components of the vectors to consider this. So this force 1, F1 here, 400 pounds in that direction, but you break it into its components. You have 400 times the cosine of 20, that would be the x component here, right there, 400 times the cosine of 20 degrees. and 400 times the sine of 20 degrees would be your y component, okay? And that would be upward. Over here, 400 times the cosine of negative 20. Now, what can you tell me about the cosine of negative 20 degrees? Thinking about what kind of function cosine is as far as even or odd. What kind of function is cosine? Odd. No. Sine is, yeah, good choice. Okay. Sine and tangent are odd functions, cosine, and then of course the reciprocals are the same. Sine, cosecant, tangent, cotangent are all odd functions. Cosine and secant are both even functions. Okay. So, if that's an even function, cosine of minus 20, what does that tell you? How does that relate to cosine of 20? Even function. Cosine of negative u, why not, is, how is that related to cosine u? They're the same. No, the odd functions are opposite. Even functions are the same. Think of how the cosine looks. Here's the x-axis, the y-axis here. The cosine function is the same on either side. It's an even function. The sine function and the tangent function are opposite on either side. So the even function is the same. So cosine of minus 20 will be the same as cosine of plus 20. And sure enough, those components are both in the horizontal, positive horizontal direction. But how about the sine of minus 20? The opposite, that's minus the sine of 20. Well, here's a plus sine of 20, minus sine of 20. Those cancel out just like our pulling on the ropes around the tree. Okay? So those go away. So what you have here is twice 400. So twice 400 is 800 times the cosine of 20 degrees. Okay? Oh, here's the sine one. Here's the y component. This is 400 sine 20 up, 400 sine 20 minus 20, which happens to be down. These two cancel out. So you have 800 times the cosine of 20. Now, cosine of minus 20 is the same as cosine of 20. And here's Ryan. Okay, we've got 4 out of 5 now, just missing Josh. Okay. So if you got your calculator, I want you to try that. 800 times the sine of 20 degrees. Now, when you're using your calculator, a great idea is to check what mode you're in first. What mode should you be in here? Degree mode.
16,000.
Say again?
16,000. Oh, never mind. I got 751.75.
Okay. They rounded up to 752. And in which direction is that?
Positive.
I direction. Positive X direction, so that would be I. So that's how they express their answer. And let's see how you write that. In figure 11-12, you can represent the forces exerted by the first and second tugboat as F1, that's the first tugboat, is 400 times the cosine of 20, comma sine 20. Magnitude times the unit vector in that direction. F sub 2, second, I'm sorry, they're going to do this. That'd be 400 cosine 20i plus 400. That's the same thing. Why? Okay, fine. You can write it both ways if you'd like. I would just do one, frankly. F2 would be 400 times the cosine of negative 20, comma, sine negative 20. Well, that angle was down. Okay? And this would be, if they write it the other way, 400 cosine 20. Now, here, they did two things here. They wrote it from interval notation to IJ notation. That's the first thing. They also evaluated cosine negative 20 as the same as cosine 20. The sine of negative 20 is the same as negative sine 20. And they've all the 400 through on both components. So that's how you wind up with this. When you add these two together, it gives you 800 cosine 20i. These add to 0. So the resultant force on the ocean liner is F1 plus F2, both written as vectors. So here's your I components together. This one, no. Here's the F1, there's the F2. And when you add them together, you add the I components, and that's 800 times cosine 20 plus 0. And that's I and 0j. And that gave us our 752I. Units, pounds. Pushing an ocean liner with 752 pounds of force. It probably will move it, but it's not going to be very fast, I don't think. Maybe being in the water, it'll do a lot better than I'm thinking. All right, any questions on that? Must have really excited Ryan. He left in no time flat. Okay. So the resultant force on the ocean liner is approximately 752 pounds in the direction of the positive x-axis. Okay? Now, another example that uses this a lot. Now, in this, you change your orientation somewhat. In surveying and navigation, they talk about a bearing. Okay? It's not a roller thing or something like this. This is a bearing as a direction that measures the acute angle. What does acute mean? Less than 90 degrees or less than pi half. That a path or a line of sight makes with a fixed north-south line. So you're always measuring your bearing, both in surveying and navigation, with a direction regard to a fixed north-south line. Now, north-south lines we usually indicate on the compass rose as being vertical. Everything else we've done, our reference has been horizontal, the positive x-axis. So that's what I mean. You got to sort of rearrange your orientation here a little bit. So, say in air navigation, but same is true in water navigation. Bearings are measured in degrees. Okay, clockwise from north. Okay, now you're going to run into a problem here if you're restricted to an acute angle. So I don't quite agree with this. The way these two statements make it seem like you can't quite. Okay. I guess they're saying in air navigation, don't follow this. In surveying and ocean or water navigation, you do it this way, air navigation that way. I guess that's what they're saying. So, not that we are, and that's all. Okay, that's all, folks. Okay, they just want you to know these two bits of information. All right, let's do example 8. And even though it's not on the slide set, it can be found at larsoncalculus.com for an interactive version of this type of an example. So, I think I'll go back to this slide because it gives me a little more white space. An airplane traveling at a fixed altitude, so it's not diving or going up, okay, fixed altitude, with a negligible wind factor, okay, that's interesting. Yeah, it's okay though. Nah, it's not. Okay. The airplane is traveling at a speed of 500 miles per hour. Thinking that may be a jet. Okay. Looks like it is one anyway. With a bearing of 330 degrees. So obviously this statement here, this is the one we're using. That one says an acute angle. 330 is not acute. Not even acute. Okay, never mind. Okay. So this is air navigation. Okay. a bearing of 330 degrees. Well, let's draw sort of our compass rose here. Okay, this being north, east, south, and west. Okay, now, always from due north, and it says a bearing of 330 degrees. Well, if you were to start here and go clockwise, remember, that was the other deal about this that's different. Air navigation bearings are measured in degrees clockwise from true north. Okay, so we're going clockwise this way, 300, that would be 90, 180, 270, and another 30 degrees would give you this bearing of 330 degrees. That's wrong. Okay, I was doing 300 degrees. Okay, well, get my pen back. That was 270, and 330 would be 60 degrees up here. So this would be the same as a 60-degree angle here. It would be 330 degrees there. Not that you need to do that. I was just showing you how far you had to go. So maybe I should take that off, though I will tend to use it, but you may not want to. Okay. All right. And they show this in the figure here. Now, the magnitude of this, that stands for the speed. That's 500 miles per hour, I believe it was, yeah. Okay. So that's the magnitude of that component. Okay. We haven't named it yet, but we could. As the airplane reaches a certain point, it encounters wind with a velocity of 70 miles per hour in the direction they're really mixing up their nomenclature here. They're in the direction north 45 degrees east. Now this is how you would be expressing surveying or water navigation with an expression such as that. Encounters a wind that would be 70 miles per hour in direction north 45 east. Notice that enables you to have an acute angle there. So this is the airplane here. So I'm going to do the airplane like this. Okay. Fuselage, I'll put a little tail on it. That's going this way. Encounters wind north 45 east. That's in the eastern direction. So that would be, this would be 70 miles per hour there. Now my 7 is not very clear. Okay, 70 miles per hour in that direction. North 45 degrees east. Okay? That's 45 degrees east of north. What are the resultant speed and direction of the airplane? Okay? That's a vector addition problem. Okay? You add this component to that component. Now the book does it one way, which is a perfectly okay way to do it. They go back to the way we've done everything before and measure from positive x-axis, which is all right. So what is that? This is 90 degrees plus 30 degrees. That would be 120 degrees. To me, this is sort of mixing them up, but it's okay. And there's the 500 miles per hour as the magnitude. Here, even though they described it this way, it can also be represented this way as north of due east, okay? And that would be 45 degrees. So this measure here is 45 degrees there. and that's a magnitude of 70 miles per hour. Okay? What would be the resultant speed and direction of the airplane? What do you think? Add by component. Now, what is the component of the plane itself in this direction? The x direction? Anyone want to hazard a guess? So let's do, say again? You may have said it right, I just don't hear well. Okay, magnitude is 500 times the x direction. What's the angle that you would use, and what trig function would you use? Cosine. 120 will certainly work. Okay. Now, frankly, and this is why I had it there to begin with, I would be just as happy using, remember I said that was 60 degrees beyond here, so I would have been just as happy to do minus 500 times the cosine of 60 degrees. But that's the same as this. 500 times cosine of 120, cosine in the second quadrant is negative, so that is going to give you the same value. And since you're going to use, well,
Why are we using cosine?
okay, good question. Why are we using cosine? You're losing the x component. And
That's why you said negative 6.
x is adjacent to this angle theta or this angle here, whichever. X is the adjacent side, y is the opposite side. And the hypotenuse happens to be 500, so the x component would be the cosine. This component here, the x component, the cosine of 120 would be the x component over the hypotenuse. Okay?
So 500 degrees is the hypotenuse. What's the adjacent?
What's that?
If 500 is the hypotenuse, what is the adjacent?
Yeah. Okay, I couldn't hear the last part. 500 is the hypotenuse.
What is the adjacent?
Adjacent, that's what we're looking for. The x component.
Do we have an opposite?
Yeah, but we'll get to that in a minute when we do the y component. Okay? Okay, so that's the x component of the airplane travel. Okay? And you know that cosine 120 is going to come out negative, so that's why it's going in the western direction. And you add to that, what's the x component of your wind? Say again? Okay, that's not 60. Remember, this was 45 degrees here. So it's 70 is your magnitude, okay, and that's in miles per hour if you want to write that down, times the cosine of 45 degrees. So this is the total, let's call it the x sub p. It's the x component of the plane, okay? X component of the plane, okay? So that's going to be times your I. We're going to get to that later. Let's do the y components. I think I'll go and put it in there now. This is times I. That's x sub p times I. What would be your y component? Any ideas? Help me, somebody. By the way, now that I've added that to it, I'm going to lose my sub P. That component was of the plane. This is plane and wind, so this is just our X component in the I direction. What's your Y component? The one 500 times the sine of 120 degrees plus 70 sine of 45 degrees. That would be your J component. And we're going to call that your Y sub J. Okay, now, do you think our signs are going to be fine? SIGN signs. What is the sign in the second quadrant? The SIN sign in the second quadrant. All students say calculus. The SIGN of the SIN of 120 degrees. Positive. Everything positive here, sine and cosecant positive here, tangent and cotangent positive here, cosine and secant positive there. So that'll be positive. How about this? 45 degrees. That's a cube. First quadrant. That's positive. So both of these are positive. Sure enough, that's certainly positive, and that one's certainly positive. So I think we got it. Okay? Pull out your handy-dandy calculators and start poking in some numbers. Actually, we don't need to do that. We know what they are, don't we? And that's why I was in favor of using what we used to call the reference angle. This is the angle 60 degrees. And what is the cosine of 60? Here, I got hiccups. Yep. No, that's sine. 1/2. Okay, so 1/2, and this is a negative. 1/2 of 500 would be minus 250. Not 252. Minus 250 plus. How about cosine of 45 degrees? Square root of 2 over 2, so I'll do the 2 into that and be 45 times root 2. Okay? This is the I component. The J component, the vertical component, that's this one. Now again, I'm going to use the 60 degrees here because that completes or supplements the 120 to make 180 degrees. And what's the sine of that 60 degrees? Root 3 over 2, and the 2 will go into that 250, so that'll be positive 250 root 3, positive again because that's still upward here, and that's going to be the same magnitude because that's a 45 degree angle. So that's, all right, y'all let me get away with that. That's 70 there, not 90. I can't read my writing. Half of 70 is 35, not 45. Half of 90 would be 45. That's 35 root 2 in the J direction. Okay? So, pull out your handy-dandy calculators. You will need them now because I don't do the square roots in my head. Negative 250 plus 35 times the root 2. That would be in the I direction. Got it? Negative 250 plus 35 root 2. Negative 200.5 in the I direction plus, I know that's going to be a plus, 250 root 3 plus 35 root 2. $482. Oh, let's make it 483J. Okay? Now, that's not what they asked for, though. It says, what are the resultant speed and direction of the airplane? What's going to give you your speed? The magnitude of those two numbers. And how do you get that? Square root of this squared plus the square root, square root of this squared plus that squared. Okay. So put those in and see what you get. 200.5. Oh, you gave me 0.5 before, so let's go back and do it. I'm sorry, I didn't notice that. Okay, 2.5 here. We'll keep it. Okay. 200.5 squared plus 482.5 squared. Get that results, hit the square root key, and see what you get. 123. Okay. So let's call this the magnitude of the total velocity of the plane is, say that one more time. 523.1. Okay. Miles per hour. Okay. And it said, what's the direction of the airplane? What's going to give you the direction? Say again? Okay, a graph will give you an indication of it, but I wouldn't trust my graph to give you an exact direction. Say again? Slope. How do you get that? Say again? Okay, yeah, if you could do a derivative here, I don't see enough variables in there for a derivative. Say again? And how do you mean that? There may be several slope formulas. I don't know which one you're meaning. Okay, you got, if we had x's and y's, that would be easy. Do we have them? Actually, let's see. No, you're right. You could do it here. If this is your y and that's your x. Okay? That would give you a slope. But how do we express that in aeronautical? What's the technique? In degrees clockwise from north. That's what we're looking for. But if you do what you just said, rise over run, that's going to give you, how is that related to your angle? Rise is y, over run is x, opposite over adjacent is? Tangent. Okay. So let's do that. The tangent of theta, if you don't mind me calling it theta, is equal to 482.5 divided by negative 200.5. Okay? So basically what we do is theta is equal to the inverse tangent of that, 482.5 over negative 200.5. Oops. Okay. Put that in your little calculator and cook it. Say it one more time.
Negative 67.4.
Now let's see. Remember though what you're doing here. That's in this negative 67.4. That would be down here. Because remember, we've been doing everything relative to the positive x-axis, which is east. That's not how we measure this. But remember, we have another issue with sines. With tangents. The tangent of this angle is also the same as the tangent of that. Remember, all students take chemistry. This is a negative angle here. Thought I wrote it down, but I guess I didn't. Can't believe I didn't write it. I just drew the line. So let me draw it in here. This angle here is negative 67.4 degrees. Is that what you said? Okay. Do you think this plane is flying down this way? No. Okay. Well, where else is the tangent a negative angle? All students take chemistry. Take positive here and there, negative here and there. Now that's not, it shouldn't be a straight line here. In fact, it should be a little longer because this was a 60-degree angle here. Here's a 67 here. So this should be a little bit greater. So it's somewhere up here, which makes sense because your component from the plane is up this way, component from the wind is this way, so it should be an angle up this way, just a little bit beyond here. So let me, I don't know where the bigger error is, but let me pretend that it's this way. Okay, so this would be the direction of the plane. Okay? So you add 180 to your negative 67.4. Now this is really convoluted because of the way they did the problem. So if you add 180 to that, okay, that gives you 112.6. Okay? That's in this direction. Okay? That's your 112.6. But remember, we're not measuring our well, yeah, they are. I can't believe they did this. They left it in those terms. Okay? So what did they get? Now, they got a little bit different number. We got 523.1. They got 522.5.
It's just because I got the same. I just rounded it up.
Oh, 200 to 201?
Yeah.
Okay, yeah. So we came out a little large. Y'all awake yet? Sorry. 4 people at home couldn't tell that was coming. Okay. Now, that would be Josh. Okay. If he's listening. Okay. Now, not now, but later. Okay. And they use that 112.6 degrees with the positive axis. Okay. What they should have done, since they were talking about aeronautical, was use this angle here, which would be to take that 112.6, subtract 90 from it, and make it, no, I'm sorry, 112.6, subtract, okay, yeah, the way they've done this is so screwy. Yeah, subtract 90 from it, and that gives you this little angle here. Subtract that from 360, and you get that angle there. But fortunately, they didn't do all that. They just left it in the numbers we got, which were 112.6 degrees from due east. And that's not how you refer to it. This was our 522.5. Is that right? 522.5. Okay. Now.
Also got 112.6 degrees.
What's that?
Also got 112.6 degrees.
That's what we got too. Yes, but then when we added 180 to it, because we knew it wasn't flying down this way. Because we were flying up this way and the wind this way, you could wind up, down here. So you add 180 to it. Whenever you're using tangents, if it's not going the way that makes sense physically, add or subtract 180 from it, or to it. Okay? And that gave us 112.6. But that's not how you measure aeronautical flight. But that's all right. They're just math people. Okay. That finally finishes 11.1. Homework exercises here at number 3. You can find that at calcchat.com. 5 or 7, they're both at CalcChat. 5's at CalcView. Any of the odds 9 through 15, all at CalcChat. 11's at CalcView. 17's at CalcChat. Any of the odds 19 to 23 are at CalcChat. 21's at CalcView. 25's at CalcChat. 27's at both CalcChat and CalcView. Odds 29 to 33 are all at CalcChat. 35 and 37 are both at CalcChat. 35's at CalcView. 39 and 41 are both at CalcChat. 43's at CalcChat. Odds 45 and 47 are both at CalcChat. 47's at CalcView. 49 and 51 are at CalcChat. 49's at CalcView. 53 and 55 are at CalcChat. You can explore or think about doing 57 and or 59. They're both at CalcChat. They should be. You can think about, do any of the odds 61 to 65. They're both at CalcChat. All at CalcChat. Any of the odds 67 to 71. They're all at CalcChat. 73's at CalcChat. And 70, I think I assigned these to you before. 75 and or 77 are at CalcChat. 79's at CalcChat. 81, 83 are at CalcChat. Any of the odds 85, these are true false, 85 to 93 should be at CalcChat. 95's a proof if you want to do that. It should be at CalcChat. 97's a geometry problem. It should be at CalcChat. And 99 is a using a vector problem. It should be at CalcChat. Any questions on 11.1? Okay. We didn't have quite all those last time, but most of them. Any questions? All right. Let's move on to 11.2. I hoped this would go a bit faster than what it's going, but all right, we'll go from current slide. All right, still in chapter 11, vectors and geometry of space. 11.2 is space coordinates and vectors in space. Now we're dealing with 3 component systems, not 2. 2 is plane, 3 is space. Okay? We'll understand the 3-dimensional rectangular coordinate system. Yes, you will. And you'll analyze vectors in space. So let's start with coordinates in space. And I think, hopefully, you're pretty familiar with this. But before extending the concept of a vector to 3 dimensions, let's first identify points in the 3-dimensional coordinate system. Okay. You can construct this system by passing the z-axis perpendicular to both the x and the y-axis at the origin. So let's just imagine that the x-axis is the one going along the floor wall line here. Y-axis going on the floor wall line here. Okay? Why did I choose them that way? We need a right-handed system. So if you point your fingers on your right hand toward the positive x direction, curve them to a positive y direction, your right thumb is pointing in positive z, and we want z going up, so that's why I chose them that way. Okay? Now, so that has the z-axis perpendicular to both x and y axes at the origin. So back here, we got sort of a big fat origin here, whatever. Now, taken as pairs, then we have planes here. That wall there is the xz plane. This wall is the yz plane. No, y'all wouldn't remember that. Okay, and then the xy plane is the floor. All right, so that gives you all those planes. Xy plane, the floor, xz plane, that wall, and yz plane, this wall. Okay. Three-dimensional coordinate system. Now, those three coordinate planes separate tree space into 8 octants. Now, I don't know how they number the octants. I've never seen them numbered, but I know the first one, which is positive x, positive y, and positive z. I call that the first octant, okay, where everything is positive. I don't know how you number the rest of them. It's positive x this way, positive y that way, positive z. So it's this one right here between the positive x, positive y, and up positive z. That's this octant here.
Positive z is going this way or going this way?
Say again?
Positive z is going that way.
Up. Positive z is up. Positive x is that way. Here's the origin back here. Positive x is that way, positive y this way, positive z that way. So this octant that we're in now is the first octant. Okay? Positive x, positive y, positive z. The one below us, I don't know what number you give it. The one out that way, you give it. The one down that way, one over that way, and the one down that way. Okay. They all have different. I've never seen them numbered. I just call this one the positive, the first octant. The first octant is the one for which all three coordinates are positive. In this three-dimensional system, a point P in space is determined by not an ordered pair anymore, that's on a plane, an ordered triplet, okay, x, y, z, where x, y, and z are as follows. X is the directed distance from the yz plane, this plane here, how far you go in the positive or negative x direction, okay? Y is the directed distance from the xz plane, this plane here, in the positive or negative direction. And z is directed distance from the xy plane, the floor, up, positive, or down, negative. Okay? So that's what these stand for. And several points are shown here. Okay? Now, here's a problem with representing three-dimensional space on a two-dimensional board. You have a lot of points that look like they're on top of each other. Okay? You almost have to have the coordinate to know what the point is. This is 1 positive x, 6 positive y, and 0 z. Don't go up or down. Okay? This is 3, positive 3 on x, positive 3 on y, but down 2. Okay? Now, why is it that plus 4? But no, it isn't. Because, again, it would look just like there, but with the lines here, you get an idea of what they mean. This one over here is negative on x, negative 2 on x, positive 5 on y, and up 4 on z. This one over here is positive 2x, negative 5y, plus 3 in the z-axis. You're dealing with ordered triplets, you need all three. Even if you're not leaving a plane, then you have a 0, like this one. Okay, you didn't leave the xy plane, so the z component is 0. All right, is that sort of making sense? That's your figure 1115 in your text and on the board too. Now, they talk about here your three-dimensional coordinate system can either have a right-handed or a left-handed orientation. I'm hard-pressed to think of anything that uses a left-handed orientation. You would think you would, because I'm left-handed, but no, nothing does. So why do they talk about it? I'm not sure. So it says to determine the orientation of the system, imagine you're standing at the origin with your arms pointing in the direction of the positive x and positive y axis, with the positive z axis pointing up where your head is. Now, I never think of it this way. And if you do, perfectly fine. Okay? But since it's handed system, not arm system, why don't you use your left hand? The left-handed system would put the, well, let me do this. The x-coordinate, that to be the x-coordinate, that to be the y, and that to be z. You flip these two. No one uses that. It's always right-handed system. X, Y, Z. Okay? And I don't know why they use arms and stuff like this.
It makes sense.
If you like it better, fine, go for it. Okay? But in this text, you will work exclusively with the right-handed system. So why even bring up the left? I don't know. Now, many of the formulas established for the two-dimensional coordinate system can be extended to three dimensions. For instance, to find the distance between any 2 points in space as opposed to on a plane, use the Pythagorean theorem twice. Okay? Here's the first. Here's a point P, which is x1, y1, z1. Point Q is x2, y2, z2. Okay? If you want the distance between those, you first, and it really doesn't matter what order you do your distance from, in the x, y plane down here, from point P to point Q in the projection on the xy plane. Okay? Now, what's hard to see here, the way they've drawn the little parallelepiped, as you might call it, the box here, they have P in that far corner back that way and Q in the near corner up this way. So you first figure this distance here of Q projected down onto the same plane the X is, the P is in, and that would be this distance here, the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? That's that square root. Okay? Now, then your length from z2 to z1, that's from here to here, to get that length is the square root of z2 minus z1 squared. That gives you that length. Okay? And then you take this length, square root of this, plus the square root of that. We'll add those together, and you wind up with, hopefully, what you were imagining and hoping. It's the distance, is the square root, huge square root here, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Just extend it one more dimension. This is distance in the plane. This is distance in space. Just extend it one more dimension. Z2 minus z1 squared. Add it together with the other two. Take the square root of that. Okay? That's easier to remember than trying to picture it on the box in my mind. Any questions? Okay? So, here's an example. From what we just did, find the distance between these 2 points. Let me get my pen set up. Okay, let me get my pen set up. There we go. All right, so what would be your distance? Square root of 1. What? What's that?
1 and 2.
Okay. 2 minus 1 is 1. Squared is 1. So that's where I got that 1. Next. And that would be 1. Okay. And plus. What'd you say? which is 25. Okay, so this distance would be the square root of,
27.
say again?
27.
27. Okay, I thought you said 47. I said, how did you get that? Square root of 27. Perfect. Okay, now you can leave it like that, but a lot of times they like to, if you have a square root, if you have a hidden square anywhere in there, take it out. Is there any hidden square buried in 27? Okay, that would be square root of 9 times the square root of 3. You're absolutely right. And what's the square root of 9? 3 root 3. Perfect. Okay. Now, let me give you a hint here, just in case you were starting to say, oh, wait, does that need to be plus or minus? Because square root of 9 can be either, right? No. Distances are always positive. Always an absolute value. So never give me a distance that's negative. Okay. And you can subtract distances from things. That would be all right. But a distance is always, by definition, positive. Okay. So 3 root 3. Let's see how they did it. Let me erase my ink. Okay. Sort of how you did it. I don't know exactly how you did it because you were just giving me numbers. The square root of, whichever you want to use as x2 and x1, it doesn't matter in distance because whatever difference you take, you're squaring it and it's going to turn out positive. So they did 1 minus 2, that's a negative 1 squared, is going to be plus 1. And then you have 0 minus a minus 1, which is 0 plus 1 squared, which is going to be 1. And then a negative 2 minus a 3, which is going to be negative 5 squared, which is going to be positive 25. So it's root 27, which is 3 root 3. All right. Now, let's do some shapes. And these shapes are going to be sort of important later. So I'm going to spend maybe a little more time on these than I should, but I think I can justify doing it. So, a sphere with the center at x0, y0, z0. Now that's not 0, 0, 0, but x sub 0, y sub 0, z sub 0. With a radius of r is defined to be the set of all points x, y, z. That's just x, y, and z components, such that the distance between this x, y, and z and that center is always that radius r. So you can use the distance formula from this statement right here. The distance between this point and that point is r, equal r. Define the standard equation for a sphere of radius r centered at x0, y0, z0. Okay? So let's do it. What is the distance here, this distance here, between those 2 points?
X sub 2 minus x sub 1 squared.
Plus?
Y sub 2 minus y.
Okay, there's no subs on that first. So y minus y sub 0 squared.
Plus z minus z sub 0 squared.
Is r. Perfect. Now, if you were saying the x of 0 minus x, if that's what you were saying, I can't hear well, that's fine too. It's not going to matter because you're going to square them. It doesn't matter what order you subtract those. I just sort of like having the variable first and the constant last, but you don't have to. You could have done it the other way. Now, what's the next thing you think you could have done? If you want an equation of a sphere, square both sides sounds like a great idea. Okay? And by the way, r is always a positive number. You can't draw me a ball with a negative radius, can you? Create one for me and throw it at me. Okay? Or even with a 0 radius. I can catch those anytime. Okay. Got it. Okay. Now, square both sides, and you get x minus x0 squared plus y minus y0 squared plus z minus z0 squared equal r squared. Now this is what they call the standard equation of a sphere. And it's perfectly fine. That's how you usually see it. I'm going to change it ever so slightly. Okay? There's a reason for it. I'm going to divide everything by r squared. Okay? And then you have x minus x0 squared over r squared plus y minus y0 squared over r squared plus z minus z0 squared over r squared is equal to 1. Later, we'll be using forms that look much more like this. So either this form or the one we have above are, I call, standard equations of the sphere. Okay? So there is how they do it. I just take the r squared and divide everything by that. Now, moreover, the midpoint of a line segment joining any 2 points here, x1, y1, z1, and x2, y2, z2, has coordinates. Okay? And here's what they are. Now this, I don't like. Because these I'm sorry, it's fine. Coordinates. This is the midpoint, 3 coordinates, not components, coordinates. I was reading that component, but it's coordinates. This would be it. So it's the average of these 2, comma, the average of those 2, comma, the average of those 2. This plus this over 2, this plus this over 2, this plus this over 2. That's it. Just the average of each dimension. Okay? That's all it is. Add the 2 coordinates, divide by 2 for each pair. Okay?
They got a coordinate of 2, or is 2 the radius?
No, 2 is the averager. You got 2 points here. 1, 2. If you had 2 grades, I said, what's your average?
Yeah.
Average, when we add them together and divide by 2. Okay? That's what this is. Average x value, average y value, average z value. Okay? That's all the midpoint is. Okay? Now, equation of a sphere is up there, midpoint formula here. They are skipping example 2. So let's go back and do example 2. Find the standard equation of a sphere that has these 2 points as endpoints of a diameter. Okay? These are points 5, negative 2, 3, and 0, 4, negative 3. Okay? Find the standard equation of a sphere that has those 2 points as endpoints of a diameter. Okay. How do you accomplish what they just asked you to do? Okay, and how do you do that? And which formula are you talking about?
The standard equation of a sphere.
Okay. By that you mean this. Okay, just tell me what you think it'll look like. Just start it off for me.
The square root of x1 minus x2 squared plus y minus y2 squared plus z1 z2 squared is equal to r.
And that's equal to r? Okay. And these are those 2 points you talked about? It's not quite what the problem said. These are 2 points, okay? Let me just get an idea. There's 5 in that direction. Unfortunately, -2 is back this way, somewhere behind that wall there, and 3 is up. So there's a point. There's a point somewhere. It's in the fan room there. 2 units back and 3 units up, somewhere back there. And the other one is 0 on X, 4 on Y, and 3 down here. Those 2 points are your end points of a diameter of a sphere that's here. Ha! Yes, you have to find the midpoint. So let's do that first. That's going to give you what? Not the radius. Well, yeah, ultimately it'll give you a radius. But what does that midpoint give you? 2 ends of a diameter is always going to give you the what? Not the origin, the center of the sphere. It's not going to be at the origin. The origin's down here. That's one fixed point. But yeah, it's the center of the sphere. So let's do that first. What would that be?
5 + 0.
I can do that. Okay, that'd be 5 halves.
-2 + 4.
Which is? It's what?
That'd be 1.
1. Got it.
And then 3 - 3 over 2. 0.
Okay. There's your center of the sphere. That's your x0, y0, z0. Got it? All right. Now you said you also got the radius out of that. How did you get the radius out of it? And there's 2 ways you can do it, huh?
The center of a diameter is the radius.
Say again?
I thought the center of a diameter was the radius.
The center of the diameter is the center point of the circle.
Half the diameter is the radius.
Half of the diameter is the radius. So how do you want to do that?
So now do you plug that
Now, yeah, that gives you your distance formula. That's the length of the diameter divided by 2. Okay, yeah, so if that's where you were heading before, I'm sorry I stopped you. Is that where you were heading before?
I was doing it too soon. I was already doing it with,
Yeah.
So I just did it too soon.
Okay, so now the other thing you could do, if you didn't want to do it that way, is take the distance either between these 2 points or those 2 points. That will give you the radius. But with fractions in that, I think I just assumed you do that. So, what is your diameter? The length of the diameter, what would it be? The square root of?
5 - 0.
Right? Say again, I couldn't hear.
5 - 0 squared.
Which is
5.
25, right? Okay. Next,
2 minus -2 minus 4.
which is?
4.
Really?
It's 36.
It's what?
36.
36. Got it. Okay. Plus
3 plus 3, which is 6, which would be another 36.
is what?
Yeah.
I
Okay.
said 3 plus 3, 6, 36.
36. Another 36. Okay. And this will be the square root of. Now I'm going to cheat a little bit here. Maybe I shouldn't. 72 plus 25. 97. Looks like it. Okay. Something just a little bit less than 10, but square root of 97. No common, no perfect squares hiding in that one, I don't think. Okay. So that's your diameter, and this divided by 2, that's your radius. By that? Okay. So what would be your standard equation for the sphere that has those points as your diameter, ends of your diameter?
So could you have done the distance formula to begin with?
Okay, if you had done the distance formula to begin with, that's what I kept trying to get while you were doing that. do that, that would have given you, the square root of that would have given you the diameter of the sphere,
So it'd be,
the length of the diameter.
the formula would be 5 halves over 90, square root of 97 over 2.
Okay. Let me think for a moment here. Yeah. What would be your equation? I can do the right-hand side. I've got that one figured out. What's the left-hand side? All right. It's what? Y minus 1 squared. Z squared. Okay, but you square it, right? 97 over 4. I think that'll do it for us. Okay? Now that may not be, nope, that's exactly the way they left it. X minus 5 halves squared plus y minus 1 squared plus z squared is equal to 97 fourths. Okay? I had thought maybe, I had hoped not, but maybe they wanted you to multiply this out and that out and that out and equal to that, and then you can multiply both sides of the equation by 4 and get rid of your denominators. It would have been ugly, ugly, ugly. Okay. So that's how they wanted it left. Good for them. We'll accept it. That's the easiest way to do it. Any questions on that? Okay. Let's see how they did it. So let me erase this. They may have done it in different order. Nope, they didn't. They did exactly like you did. First find the, on the second or third try anyway, take the length of the diameter is the square root of that squared plus that squared plus that squared. And that would be square root of 1 plus 1 plus 25. That's square root of 27, which they said is 3 root 3. Did we say that? I don't think we did.
This is example 1. We're doing example 2.
Wait, that's example 1. You're absolutely right. Let's just look in the book and see what they got for example 2. No, we had already done that. Yeah. Forget that. Okay. Don't forget it, but you know. All right, now let's move to vectors in space. Okay? In space, vectors now are denoted by ordered triplets, not ordered pairs, ordered triplets in vector notation. Guess what the zero vector is? Zero, zero, zero in vector notation, in vector angle vector unit brackets, okay? What are our 3 standard, well, they're doing it. Let's go to them. In space, well, say it and then say it again. Vectors are denoted by ordered triplets. Say vector V, notice how bold that is. I can't write bold, so if I were doing this, I'd put an arrow over it. Its 3 components are typically given as V1, V2, V3. Angle bracket, those are components, not coordinates, components. Those are parentheses, those are coordinates of a point. Angle brackets, those are components of a vector. Zero vector, that would be the zero vector. Again, bold, I would draw it with an arrow over it. and its components are 0, 0, 0. Two problems with the zero vector, has no magnitude and no direction, so it's the only vector that doesn't. Okay. Then, using the standard unit vectors, they are I, which would be 1, 0, 0, J would be 0, 1, 0, K would be 0, 0, 1. Notice all we've done is add an extra component here, extra component there, and extra components there, there, and there. These two components being 0, that one being, the first two being 0, the second 1. The standard unit vector notation, okay, to me, well, okay. What they're calling that, I call it IJK notation, because if you had done, well, let's just say, standard unit vector notation, vector V would be V sub 1. Now, see, V sub 1 is not a vector, it's a component. So this V sub 1, that V sub 1 are the same. I plus V sub 2, J plus V sub 3, K. Okay? This is vector V in vector notation, vector component notation. This is vector V in what they're calling standard unit vector notation. Okay? And here's what we mean by that. So I vector is 1, 0, 0, J is 0, 1, 0. Frankly, to me, it looks like J is longer than I, but I is foreshortened because it's coming out of the board. And K should be about the same as that one, so that's 0, 0, 1. So any other vector, now this one happens to be in the first octet, all positive, would be V1 out here, maybe right along in here, V2 over here somewhere, and V3 somewhere there. Okay? Well, no. There. Okay. Sort of bizarre looking. That's the standard unit vector in space, V1I plus V2J plus V3K. So that should be 1, V2, V3. And just looking at this, it looks like V1, component V1 is a little bit greater than 1, may be coming close to 2, okay? V2 looks like it's pretty close to 1. It could be 1 on the nose. It looks like it could be. And your V3 here, that's the one that's a little confusing because this base drops down to here. You would have to take that length, transpose it up to there, and that looks like it would be at least 3, maybe even 4, or something between 3 and 4 up there. So that would be your component, V1, V2, V3 by components, and also by standard unit vector notation. If V is represented by the line segments from P to Q, where P is up here, P1, P2, and P3, which happens also to be in the first octet here. P1, very short P2, and a reasonable P3. And Q, the point Q, is further this way on X. Sure doesn't look like it here, but it is. It's this vector is pointing this way on X, further that way on Y, and certainly a lot longer on Z. And V is the vector between those 2 points. Then what we can say is vector V, its X component, or its first component, is Q1 minus P1 in the I direction, Q2 minus P2 in the J direction, and Q3 minus P3 in the Z direction. Okay? Now looking at that, this minus this here is a small X direction. That's a little bit larger Y direction and quite a bit larger Z direction. So this vector V is coming further out, just a little ways out on X, a little bit more on Y, and quite a bit higher on Z. So hard to get a perspective of that vector. If they draw the things in here, you get a good one. But without these points here, you don't have a clue where it's going.
They're vectors, right?
Yes. Hey,
Hey, Dr. Pope wanted me to remind you that contracts are due today.
we talked about it Friday, and he said, don't worry, we'll do them next week, next Friday.
Yeah, he said Crawford told him today.
Okay. I told him it was going to happen. I said, they're going to ask for, I was saying by Wednesday of this week. Now they're saying today. Why didn't they tell us Friday? We were right there. We could have done them all Friday. Okay? So, I'm not going to be out of class until 3:45. So.
Okay, they're already past this.
What's that?
They were due at noon, so it's already late.
I'm really worried about it. Okay, thank you so much. Okay. Yeah. What's that? Oh, we're out of time?
No,
Wait, you should have a much sadder look on your face when you say that. Okay, that's better. Okay. Wow, are we? All right. Okay. So there is vectors in space. That's down to here. We'll start next time with the vectors in space block right there. And let me erase this.
Mr. Fowler, were those all vectors? Because I noticed you're going from component to coordinates.
What's that?
I noticed you're going coordinates to components to
Yeah.
coordinates. and
These
that's
are
confusing.
coordinates here in parentheses.
Yeah, but those coordinates went into.
When you take
They
the
went into
difference in
J,
these
I,
two,
K.
that gives you a component.
Oh, really?
Difference in these two gives you this component. Difference in those two. Now, in these, back when we were doing the distance, it didn't matter what order you get. These, the order matter. Always Q minus B. Terminal minus initial. Always.
Terminal minus initial. Terminal minus initial. Terminal minus initial. Okay.
And Q is almost always terminal and P initial. All right, we didn't get very far there. Whoa, it's a very short section. Homework exercises here could include 5 and 7, or 7. They're both at Calc Chat. 9 or 11 are both at Calc Chat, 9 being Calc View. And let's just end on there. We'll pick up the rest of those next time. All right, good deal.
See you Wednesday.
All right, see you Wednesday.